Pleasure to have Raphaël Côte from Strasbourg University, who is going to talk about multi-soliton dynamics for nonlinear Klein-Gordon equations. Please.
Well, thank you. Thank you for the introduction. Thank you for this invitation. I couldn't come to visit in Abu Dhabi, but I'm very glad to
maybe next time.
Sorry, do you hear me well? Maybe that was
yeah. Maybe next time, I said.
Maybe next time, yeah, hopefully. So I will talk on a project that has started maybe 3-4 years ago with Lifeng Zhao, in fact. And then so Lifeng was a postdoc at École Polytechnique with Yvan Martel. And then Yvan joined. So Yvan is a professor at Polytechnique, and he joined with his former PhD student, Su Yuan. And what I will be discussing is a part of Su PhD. And Su is now in Hong Kong. Actually, he's in a postdoc in Hong Kong. Okay. So let me first do a little introduction on dispersive PDEs. So I gave a few models. Do you see the mouse when or not?
Yeah, we see everything perfectly.
Okay. Very good. So I give a few models of a nonlinear dispersive PDEs. So you see Schrödinger types model with some power nonlinearity, wave type models with the same kind of nonlinearity, and I also mentioned in one space dimension quotevectorist types model with a slightly different nonlinearity, because here there is a derivative. And so this kind of equation, they all share the similar features, like you have a linear part and a nonlinear part. And if you focus on the linear part, what you can see is that if you try and find plane waves for like formal solutions, they do not belong to L2, but if you try to look for plane wave solutions, then they're of this form. So this is a plane wave at frequency psi, moving with speed omega. Then the speed depends on the frequency. So this is a sharp contrast with, for example, transport equation or maybe the heat equation. And we say that it's dispersive when the dependency is not trivial, when you have an actual dependence. So different frequencies are transported at different speeds. Okay, and this means by typically a stationary phase argument that the linear part, a solution to the linear equation, will tend to 0 in maybe L infinity, even though it preserves its L2 norm and more generally the HS norm. And so what does it mean? It means that a solution to the linear equation has to spread. And typically wave equation will spread on the cone, on the light cone. So at time t, they will be concentrated on the sphere of radius t. Schrödinger type solution will spread on the on a parabolic parabolic model, and so on. Okay, so this was for the linear part, and for the nonlinear part, so I will focus on the power nonlinearities, and I put this sigma. So sigma is a constant here, and so it's a sign actually. So for all these equations, there is a scaling, so you can choose after changing the scale that sigma is plus or minus 1. And for this equation, -1 is defocusing, so it means the nonlinearity helps dispersion, and what you expect for the dynamics is that the dynamics of the nonlinear equation mimics the dynamics of the linear equations. Whereas if sigma is +1, you're in the focusing case, and in this case, you have somehow a balance. The nonlinearity goes against the linear effects, and you have supposedly a richer dynamics. And I will essentially speak about the focusing case. And so dispersive PDEs usually are simplified models, reduced model for more complicated physics phenomenon. So the idea is to capture one physical model in the limit of some small parameters in some very specific regime. And when you're in the focusing case, you're really interested in traveling waves and solitons. So I will discuss this. And one of the big questions in dispersive PDEs is what can you say for about the long time behavior of solutions. Okay, so today I will focus on the nonlinear Klein-Gordon equation, which is a wave type model, which you can see here, like dTtu minus Laplace u. So there is a mass term, the u, there is the nonlinear term, f, which will be a power nonlinearity, and there is this term that I will discuss a bit later. So I'm working in the full space Rn, dimension n. And this is a model in quantum field physics for self-interacting scalar field. So it's a baby model, say, in like a general relativity. As I mentioned, it's a nonlinear wave type equation with, I choose the minus sign here, so it's focusing nonlinearity, and there is a mass term. So to the contrary of the equation on the previous slides, there is no scaling. So this u term kills the scaling. Now let me say a few words about this term, 2 alpha dtu. It's a damping term. So alpha is a constant parameter in this discussion, non-negative. So if alpha is 0, there is no damping. So it's just nonlinear Klein-Gordon. And if alpha is positive, then there is damping. And I will put a small d in front, d and LKG. I will mostly talk about the damping case because it's where my talk is focused, but I will mention a few results in the undamped case. As it is a wave equation, you still have finite speed of propagation, which I will not really use here. So even in the damped case, here speed of light is 1, as you can see from the c squared here, which is 1. And in the undamped case, you have an extra invariance of the equation besides space translation, space and time translation. You have Lorentz transform, and I will say a few words about this later on. Okay, so about the nonlinear term, keep in mind that p equals 3 is the most physically relevant nonlinearity, but at no great cost. We can look at H1 subcritical nonlinearities, that is p bigger than 1 and less than n plus 2 over n minus 2. And at some point, I will ask that p is greater than 2, strictly greater than 2. And I would like you to bear in mind that actually p equals 3 is really the nonlinearity I'm interested in. Okay, let me write capital F for the antiderivative of little f. Which will play a role in the energy. And at many places, I will use a vector formulation for this equation and not only look at u, but at the vector u dtu. So when I put a little vector, it's just the 2-component vector u dtu. And so I have the equations here. Okay. Okay, so when you want to study an evolution equation like this, the first question you can ask is whether the flow is well defined, at least for small times. So you want to solve the Cauchy problem, and this has been done in the 80s and improved in the early 2000s. So you only need to know that both equation, NLKG and the damped NLKG are well posed in a strong sense in HS cross HS minus 1 for any S greater than 1. And most of what I will be doing will be for S equals 1. And what does it mean? It means that if you give yourself an initial condition, initial data, U1 in HS cross HS minus 1, so it should be N here, not T, sorry. Then you can construct a continuous solution, which is defined on a neighborhood of 0. And especially in the damped term, I will be interested essentially on what happens around T plus. So T plus is the maximal time of existence. and it's continuous, which with value in HS cross HS minus 1. Yeah, and okay, another typo. U naught is the vector U naught is U naught U1, of course. And furthermore, the map is smooth. Okay, so there is a blow-up criterion. If T plus is finite, then actually the H1 cross L2 norm tends to plus infinity. Not only the HS cross H minus 1, but the H1 cross L2. So actually the blow-up time is actually the same for every regularity index S. And yeah, I will only use well-posedness for S equals 1. But actually it's well-posed till the critical exponent, which is SP, and which is less than 1, because we are looking at H1 subcritical nonlinearity. Okay, and coming with the local well-posedness, we have two, so they're not conservation laws, but they are quantities of interest. They are conservation laws, the energy and the momentum, E and P. They are conservation laws for the nonlinear Klein-Gordon equation, that is when there is no damping. And when there is damping, actually the derivative of the energy is 2 alpha the dtu in L2 squared, and you have a similar ODE for the evolution of the momentum. And okay, so with damping, I like to write it like this in the integrate way. And let me mention that as the nonlinearity is focusing, actually the energy can tend to minus infinity. And actually when the energy is negative, then finite type blow-up occurs. So you don't get for free, for example, that you have an L2 bound, an L2 bound on DTU. Well, still I will rely a lot on the energy dissipation identity. Okay, so what about the large time behavior? So if you're not interested in the in a precise dynamics, then there is a few things that you can say right away. So there is ODE blow up, and this is really easy to see. You can see it by using finite time, finite speed of propagation, and you just take a function in H1, which is a constant on a large ball, and then goes to 0. So it has to be in H1. Then on the cone, on the light cone, the inner light cone coming from this large ball where the solution is a constant, then it's also a constant which solves the ODE, and you can see that the ODE admits finite time blow up. So by finite speed of propagation, it cooks you a lot, a huge lot of blowing up solutions, and even though there is damping. Right? So the damping is nice. You could say, okay, the damping will prevent me from blowing up, but actually it's not the case. And you have ODE blow up, and also this ODE blow up tells you that it's like a really you can't tell many things about it, because really you can do whatever you want somehow away from this large ball. So the ODE blow up is actually not so interesting to study. There is another kind of finite time blow up that one can have is for negative energy initial data. The energy of U naught is strictly negative, and by virial type argument with a convexity, you can show that actually well, you do have finite time blow up. Okay. And for the large time behavior, there is this general conjecture that tells you that global solution should in turn have a behavior which is much more constrained. And it tells you that global solutions should behave, at least for most data, I put generically, it should behave as a sum of decoupled nonlinear objects, like which preserve their shape, up to some term, term vanishing in some sense. So I will detail what the object, what the sollten conjecture should be in the Klein-Gordon case. Yeah, this will be on my next slide, but soliten are meant to be these special objectives. So there are special traveling wave solutions. And in the damped case, actually the damping kills the Lorentz transform, and they're no longer traveling. So you have solutions, but only stationary solutions. So soliten should be the stationary solutions. Okay, so let's talk a bit about the stationary solution. So you take the equation and you put dtu equals 0. So dt squared u is also 0, and you're left with this elliptic equation. And so it has been studied a lot. We are in the H1 subcritical case. And you know that any non-trivial solution, well, 0, 2, but any non-zero solution is smooth, as smooth as the nonlinearity allows. And here P is 1, so it's at least C3. If P is an integer, it will be C infinity. And it's exponentially decaying with a fixed rate omega naught. They all have, any solution have the same rate. And now among these, so there are a whole bunch of this kind of elliptic solutions, and actually some are better than others. The ones that are better than others are the ground states, who are actually solution of the elliptic equation that actually minimize the energy, or at least the kinetic part of the energy, E of U. Right, so I call G the set of ground states, which is, as I mentioned, the bound states that minimize the energy. So they do exist, and you can classify it. So it's a very important result in the pure power case. You can tell that ground states are actually the translation or a fixed profile Q, which is radial and positive. So it's H1, radial and positive. Well, it's much more than H1 because you have also exponential decay, but it's positive. So this is a big criteria. And so Q solve, if you see it as a function of the radial variable, then it's solve an ODE, and it allows you to have this expansion. So you have you have the correct expansion at infinity, and in dimension n, you see that you have this exponential decay. And it's slightly improved by this polynomial decay. So in dimension 1, it's really exponential. And actually the error in dimension 1 is better. It's exponential minus r plus big O of exponential minus 2r. But when n is bigger or equal to 2, then the second term is not as decay. So you just gain 1 power of r. Okay, so this is also specific to the power nonlinearity. I think you have Manuel Del Pino, who comes to talk later on this year. I don't know what he will be talking about, but he worked a lot on this kind of things. And when you choose other nonlinearity, you can cook up examples where you have where the ground state are not so easy to get. You don't have this kind of uniqueness. Okay, so in dimension 1, you actually have an explicit formula for Q. So, and you can get the decay. So I guess, so you get it by ODE methods, and then I guess it goes back at least to Boussinesq. So it's second half of the 19th century. However, and there is no other ground state, well, bound state than the ground state. In dimension greater or equal to 2, actually, you have a lot of bound states. So ground states are always a strict subset of bound states. And okay, I will talk a bit about bound states which are not ground states, that is excited states. And there were many papers, as I mentioned, that construct excited states. So you can build radial excited states that change sign. That was done by Berster-Kilian. So they did two papers. The first paper was existent of one, and the second paper was existent of plenty, but all radial. And if you're looking at non-radial, they do exist too. So it's you have several papers by Delpino, Musso, Paccard, and Pistoia. And you can also have, for, as I mentioned, for nonlinearity that are non-pure power, typically that are a sum of pure power of pure powers, then you have positive excited states, radial and positive excited states, which are not the ground state. Now, this is Davila, Delpino, and Guerra. Okay, so as soon as you leave dimension one, then you have the zoology of bound state becomes really, really complex. Okay, now let's talk a bit about solitons. So what we did before was looking at stationary solutions, and when you're in the Undon case, I mentioned that you have the Lorentz transform that I wrote here. So basically, if you give yourself a speed beta with norm less than 1, then you get a new solution via this Lorentz transform. And for stationary solutions, it gives you a solution of this form, right? So it's simply a traveling wave with speed beta. So for any speed less than 1, strictly less than 1, you have a traveling wave with that speed. Okay. And actually, you can prove that any traveling waves are of this form. So they're a Lorentz boost of the stationary solution. So this is specific to the Undon case, right? I mentioned already that in the Dun case, you do not have a traveling wave solution. Okay. And the soliton are traveling waves where here you have Q, which was only a bound state. And solitons are traveling waves based on ground state. And in the physics terminology, solitons are usually referred as stable objects. However, for the Klein-Gordon equation, and even in the damped case, solitons are, well, what I call solitons are linearly unstable. However, I will still speak about solitons. Still, this instability tells us that, well, for the dynamics, there will be a lot to be said, right? And the instability is really, it's not an algebraic instability. It's not like linked to criticality or anything. It's really deep in the equation, and it's actually linearly unstable. So if you look at the linearized operator around the stationary solution Q0, then for the error, for the extra term epsilon, then at the linear level, you have this equation in vector form, where L is this operator minus Laplace plus 1 plus f prime of Q. So this is the linear operator of also the potential energy around Q. So it's a very important operator. And for this operator, you see that it's, so as Q is decaying and f prime tends to 0 at infinity, this is a compact perturbation of this operator. So it has essential spectrum 1 plus infinity. It also has an eigenvalues, but not in the spectrum, not in the continuous spectrum, which are made by derivatives of Q. So this is linked to the invariance of the equation via space translations. And actually, L has one eigenvalue, negative eigenvalue minus nu naught squared, with an eigenfunction y. Okay, and and if you defined y plus the vector y plus being like y nu plus 1y, then this guy is a solution to the linearized problem. And you see that nu plus is actually positive. Nu plus minus are given here. Nu plus is positive, so you have a linearly growing, exponentially growing in time mode. So it's a strong instability. Okay, so well, from the point of view of dynamics, it tells you that well, there is work to be done, right? Okay, So in the talk, I mentioned multi-soliton in the title. So multi-soliton are just solution to the nonlinear equation that behaves as a sum of these soliton, and you want them not to interact too much. So you will ask that they have that the center of mass is far away from one another. So multi-soliton is just a nonlinear solution, which is the sum of these soliton solutions, and with the center bt bk minus bj tending to infinity. And they're very important in the long-time dynamics, because somehow they're solutions that do not disperse. So it's not like a soliton which really keeps its shape, but it's almost like a soliton, right? There is no energy, well, dispersive terms going around. When the speeds are really different, that is, so think of the Klein-Gordon, Untitled Klein-Gordon case. If the speeds are different, that is the distance between two centers is of order CD. You speak of weak interaction, and they are the stable, what you expect to be the stable multi-soliton. If it's a little O of t, then you speak of strong interaction, and what happens usually is like you're far below little O of t, you're in log t somehow. And then you can see why you speak of interaction, of weak and strong interaction. If two solitons are at distance ct, then as they have exponentially decaying tail, then the interaction, say q index k times q index j, is of order exponential minus some sigma t. So it's an exponential decaying term in time. So it's very weak. However, if you're in log t, then the interaction is in some 1 over t to some power, and it's much stronger. Okay, so it's multi-solitons are important, especially in view of the soliton resolution conjecture, which tells you that actually multi-solitons are somehow building blocks of generic of the long-down behavior for generic solutions. And there have been a whole bunch of papers on the on constructing multi-soliton. So it started with a Mel in 90 for NLS in the L2 critical case. Then Martel worked on the Korteweg, Korteweg equations. And yeah, and we extended with Yvon and Franck to the L2 supercritical case. And let me so there are really a lot of work. Let me also mention the work by Ming, Hussein, Svetkov on the water wave system, which is no longer a completely reduced model, but a more water wave systems are much more involved than the usual dispersive equations. So these were all results for weak interacting multi-soliton that are sometimes meant to be stable, except when you look at the supercritical case. In the supercritical case, they're not stable. And then more recently, there have been results on strong interacting solitons, starting with the work of Raphaël and Raphaël and Yvon Martel for NLS and Guyenne. And we can mention also a bit earlier, there was a paper by Merle and Martel, but in a slightly different context, but still with strong interaction for the wave equation. So for the wave equation, you don't have exponential decay, but you have polynomial decay for the critical wave equation. And so it's not soliton, and there are distance C of t, but the interaction is algebraic. So yeah, maybe that was the start of the thing. Okay, so after this long introduction, I can state my results. So so there's a lot of results. Maybe let's focus on the one that I'll try and give you some ideas of proofs later on. So it's a result with Yvon and Sue for the 1D case. All right. So in the 1D case, we can treat any nonlinearity bigger than 2, and especially 3, and it's in the damped case, of course. So we say that any global solution with a finite energy, any global solution, because with initial data in H1 cross L2, we can describe its behavior. So either it converges to 0, either it converges to 1 soliton up to translation, or minus a soliton. And in this case, in the 3 cases, the convergence is exponential. Right? Or it converges to a sum of alternating solitons, finite sum of alternating solitons. So you choose one sigma, and then it's alternating, and it converges with an algebraic speed t to the minus 1. And well, we did not push the analysis completely to prove that it's actually in most cases an equivalence, but you cannot do better than t minus 1 essentially. And furthermore, we can really describe where the center of mass lie, and it's the behavior is really universal in some sense. So if you have k soliton, then zk, the leading term is in log t, and what you must see from this factor is that the distance between one soliton and the next, so it's just changing k plus 1 and k, is the distance is log t. The distance between 2 solitons is log t. Then you have a universal constant, tk, which is independent of the initial data. Then you have an L, which corresponds simply to the invariance by translation. And then you have a lower order term, and these one are no longer universal. But you see that the first 2 terms here are independent of the initial data. Okay. Okay, and beta depends on p, is positive, and essentially it's like the minimum of p minus 1 and 1, say. And we have a second theorem that tells you that, okay, all the possibilities here occur. So in the first case, it's really easy because you just choose sigma q. And in the second term, you really have to build these solutions, and you can see that you do not have better than t minus 1 for the solution that you built. So, but they do exist. So in some sense, the classification is complete. So let me give some comments. So this result really tells you that for the 1D damped nonlinear Klein-Gordon, you have the full soliten resolution. This resolution, this conjecture was formulated after a numerical work by Zabriskie and Kruskal in the 60s. And in integrable case like KDV or NLS, cubic 1D NLS, you can use inverse scattering method, which works for smooth and decaying data, and you do obtain a soliton resolution. So that was one of the great success of the inverse scattering method. The drawback is that you have to choose really nice initial data, and also it's really sensitive to perturbation of in the nonlinearity. As you need to have lax square, you need to be in the integrable case, and everything falls down if you look at perturbation of these guys. So there have been a whole program to make some progress in non-integrable cases, and progress was made for wave type equation. And I quote two kind of works by Drucker scaling Mel for the energy critical wave equation, and for a related system, the equivariant wave maps. There have been some works by Koenig, Carlos Koenig, Andrew Lowry, and Wilhelm Schlag, and myself. And ending with this nice paper by Jacek Jędrzejczyk and Andrew Lowry, which somehow solved the soliton resolution for equivariant wave maps. However, it's really linked to wave equation, and even if you look at a wave equation which is slightly different, which only differ through the mass term actually. It really completely kills the construction. So it seems really out of reach for the undamped Klein-Gordon equations. Still, in dimension 1, we were able to work this out. And actually, we have a really complete description, because we not only say that, okay, for large time we have some kind of description, but we have a very precise asymptotics on the free parameter, that is the center of the mass of the solitons. And also we tell that you can't do better, because given the parameters, then you can construct a solution. So really it's complete. And so the natural question is, what can you do about higher dimensions? Could you do the same? And the answer is, then you run into a lot of problems. You have at least two new problems. The first is that in dimension 1, you only have solitons, bound states or only ground states. But in the high dimension, then you have to understand excited states, and it can be a mess. And the other thing is that you need, once you decouple the soliton dynamics from the remainder dynamic, so the remainder dynamics is meant to evolve in an infinite dimensional space, and the soliton dynamics is in a finite dimensional space. So when you decouple these two evolution, you still are left with the system for the soliton centers, and in higher dimension, ODs can be also very complicated. So the behavior is really hard to understand. Okay, still, I can give you some other results for simpler cases in higher dimension, and actually it's how this whole program started. So we started with looking at two solitons. So our first goal was to look to describe two solitons, and then we understand that somehow there was some kind of stability around two solitons, and so you have to be careful with what you say, because there is still finite time blow up for initial data, which is a near sum of two very separated solitons. But if you assume that at least for a sequence of times, your solution is near the sum of decoupled soliton, that is a sum of two solitons which are far away from one another, the center Z1n and Z2n tends to 0. So if this occurs for a sequence of time, then it actually occurs for all times, right? So you have continuous function Z1 of t, Z2 of t, such that this decomposition takes place. It not only tends to 0, but you have a decay rate. You can say that they have alternative signum, and once again, the distance between the two solitons is really universal. So you have this log t. So you have to imagine you have the center, and the center is okay. So there is a plus missing. So it's z infinity plus this guy. So the center of mass of the whole solution is d infinity, and then at distance half log t on one side and half log t on the other side. With direction omega infinity, you have the other one soliton, so they're at distance log t, and you have a correcting error in log t. Remember that n is greater than 2. So if you actually the theorem works also in dimension 1, but in dimension 1 we have a much more precise result. But in dimension, it's not, so it's okay with what I told you about dimension 1, because this term disappears in dimension 1. And so you have a very precise description of the center of each soliton. Okay. Okay. And okay, so this is some kind of, I would say, stability results, and we can be more specific. So I will maybe not give you the full details of this of the theorem. Just you can read the text behind, which tells you that the point is that if you start around very separated two solitons near that, then you can completely describe the initial data, which will lead to two solitons, two solitary waves. And it's actually a codimension 2 Lipschitz manifold. And the unstable direction are given by the y plus, so the unstable direction around the soliton, around each soliton. So each soliton carries one instability direction, which is only normal. Right. So this classified the two solitons, and actually it was inspiring for Ishizuka and Nakanishi, who improved the results and give a full description of the damped Klein-Gordon flow around a sum of faraway solitons. So what they prove is that if you start as a sum of, so you know that the sign must be alternating if you want something, if you want to be, well, if you have the plus sign, then you enter, you can prove that, well, we can describe the behavior from our previous work. So they were interested in what happens if the two solitons have the opposite sign, and you assume that they're far away from one another, and that they have a small accident phi with a small energy node. And they show that you have several possibilities, and every one is possible. And there is a description, a precise description that I don't give here on what happens where. And so, of course, it can blow up in a finite time, or it can converge to 0, 0, or it can converge to one soliton. And here you have to understand that if you converge to Q plus, it means that this one remains and this one goes to 0. If it's minus Q, then this one vanishes and this one remains. And it can be a two soliton. So what we did was this, and Ishizuka and Nakanishi completed the picture with the other three possibilities. Okay, so this was for soliton. And as I mentioned, the point is that when you have only two objects, then the equation, the ODE system for the soliton center is actually really an ODE. It's not an ODE system, it's an ODE. So it's easy to understand. And when you have at least three, then you have an ODE system. And it's at least 3D. So, well, many things can happen. So this is why we can tell things about two solitons, but three solitons seems really much harder. The next question is, what if you want to consider excited states? And let me mention actually the theorem by Burke, Rogel, and Schlag that prompted us into looking into the damped LKG, which tells you that for radial solution, then it either blows up in finite time as usual, or it's global. And if it's global, it either tends to 0 or to a bound state, to one bound state. So this is for dimension between 2 and 6. Of course, in dimension 1, as we saw, you can converge to, you can be a multi-soliton. And when we ran into this result with Yvan, we thought, okay, now we have a. So the proof really relies on a dynamical system in infinite dimension, right? And they really only get convergence, but not at all the description of how this works. And when we first saw this paper with Yvan, we thought, okay, we probably can be much more specific and describe much more precisely what happens. And that was our goal, and that was our starting point for studying two solitons. Now, if you look at excited states, then the convergence, even to one excited states, can be very slow. If you look at the theorem below, you see that you can construct a global solution which converges, so it's not Q, it's Q0, which converges to an excited state, and the rate is exactly t to the -1. So here, the fact that you do not have exponential decay is in fact some kind of self-interaction on the excited states over itself, and it already kills the exponential decay. So it tells you that before, essentially, at leading order, what was important was the interaction between two solitons, which you can study somehow. Here, it will tell you that already one soliton can give you trouble. So there is some definition, because we were able to prove this result for a very specific kind of excited state, which we call degree 1. So a degree 1 excited state is the point is, what is the kernel of the operator of the linear operator. So this L should be the same L. Sorry about this. So we remember that the L is this one. Oops, cannot seem to be okay. LQ is minus Laplace plus 1 plus minus f prime of q. This should be a minus. So you know that the kernel has to be quite large. So it has to have the derivatives, the space derivative of your excited states. But also you have rotation that acts on the equations. So you have to look at angular derivatives at the omega ij. So you have, so if q is no longer radial, of course this is not in the space, so it can be much bigger, right? Q could have some symmetries around some directions, for example, but still, so it means that these guys would be 0 for some I and j's, or some combination of I and j, but you still have to look at them. So this is really the space related to the invariance of the equations. And what the thing is that if these directions span the kernel of the linearized operator, then it's non-degenerate, and in the non-degenerate case, we're able to prove exponential convergence. However, if it does not span, if ZQ does not span the kernel of LQ, we say that it's degenerate. And if you look at the simplest case, which we call degree 1, that is the linearized operator is spanned by ZQ plus only one direction, and this direction is generic, is not degenerate either, in the sense that this quantity is non-zero, and this quantity is actually the third order term. So we need to have the third order term not zero. Then you can cook up a solution as in the theorem. So actually this kind of thing happens for the radial solution, because this is one of the important points in the radial case. In the radial case, you're either non-degenerate, or either you have a degree 1, right? You have this equality. What is harder to check is this non-degeneracy condition. But if you have this non-degeneracy condition, then we're able to improve a lot this convergence. We're able to prove this kind of result for any radial solution. Okay, and if you assume that you're degenerate, then you could push the analysis further, but then the rate of decay would be even slower. Okay, so these were all the results that I wanted to talk about. Oh, okay, so I spent a lot of time on the results. I wanted to say a few words, but it will be very short, unfortunately, on the main results, and explain to you a bit how it works. So yeah, the idea is how you prove this kind of convergence. So maybe not the convergence of the ZK, but maybe the fact that you have alternating signums, and yeah, and the T-1 convergence. Okay, so I put the theorem, and okay, so I started with a finite energy global solution, and the starting point of all this work is this result. It's an old result based on a concentration compactness argument, which tells you, so it's not dynamical at all. It's for a sequence of near solution of an elliptic equation, of the stationary equation. which is minus Laplace un plus un minus f of un, and you assume that it tends to 0 in h1 minus 1 in a strong sense. Okay, so you give yourself a sequence of h1 functions such that the energy is bounded. Recall that it's not always the case for Klein-Gordon, for the nonlinear Klein-Gordon equation. The energy can tend to minus infinity. And if you assume this, then actually the energy is bounded in h1. The sequence is bounded in h1, and up to a subsequence that I still denote un. Then un is actually a sum of stationary solutions. So you have bound state, decoupling at infinity. So the center is in white K, and the convergence is strong in H1. So it's a this kind of result. So it's here we're in the subcritical case. So it's a somehow perfect result. This kind of results were much improved in the energy critical case and lead to the profile decomposition of Gérard and Baury, the Baury-Gérard profile decomposition, the Merle-Vega profile decomposition. But in the subcritical case, it's much easier actually than in these papers, and you have really the most you can expect for. Because if you have a solution which is of this kind, plus an error term in H1, then of course it satisfies this. Okay, so this is the starting point, but we're not there yet because we don't know that the energy of a global solution is bounded, and we don't know that this occurs even for a sequence of time. So this is the purpose of the two results, which tells you that in dimension one, if you have a global solution, then its energy is bounded, and H1 cross L2 norm is bounded. So it's even better than what you need for the concentration compactness results of the previous slide. And this is mainly done by Cazenave. So Cazenave did the undamped case. For the damped case, you have to adapt. So you have to add this term essentially. And it's essentially convexity arguments on these two quantities, right? So this is essentially the energy, the linear energy, and then you have to mix this argument with a trick found by Ferezel, who tells you that even so this is very specific to dimension one. It also works for higher dimension, but then you have to be the exponent has to be much smaller. It has to be subcontrollable. But Ferezel trick works for any dimension. It tells you if you have a global solution, then actually, if this global solution is bounded in the H1 cross L2, as given by the Cazenave proposition, then DTU tends to 0 and DTTU also tends to 0, right? So you're exactly in the position where you're looking at the stationary solution plus an error, right? So you can apply the Public theorem for any sequence. Not only one, but any sequence. Okay, so where do we stand at this point? We know that for some sequence, U of Tn tends to this sum of soliten, which is, so the signums here are, you don't know, plus or minus 1. So you're in dimension 1, so you know that all the bound states are only excited states, which is very nice. But the signums are, you don't know what. You don't know anything about the signums. Okay. Okay, so maybe I go a bit fast. I recall the instability direction, which is the y. And instead of working with the y, you can work on the adjoint problem. So you look at the z and the coefficient epsilon. So epsilon is the linearized error. And if you look at a, then a satisfies an ODE with the growing norm or growing terms or decaying terms. So this scalar product somehow drives the dynamics around a solid. Okay, so where we stand is we have this decomposition for a sequence of time, and we have to prove that the solitons are alternating, and that the major work is to prove that this decomposition not only occurs for a sequence of time, but continuously in time. Okay, And this will be done through actually a stability result. So the idea is to look at the maximal interval on which you have the decomposition. So this is the content of this hypothesis. You look at an interval of time on which you can decompose with a small error gamma. You can decompose U as a sum of soliten. And of course, here you will not, the sign of fixed on this interval of time. What can move is the center of mass, and you will ask that the center of mass remain sufficiently separated. Okay, so you work on this time interval, T1, T2, and the first thing you can do is you can modulate the psi into a zk. So you change a bit the center of mass, and you add also a little thing on the derivative, and in exchange you get some orthogonality conditions. So this can be done very simply. It's an application of the implicit function theorem in finite dimension, where you just impose this condition to hold. And the good point is that you can derive the equation for the zk and the lk. Okay, so what are the equations? So first you write the equation for epsilon and eta. It write like this. So eta is essentially the time derivative of epsilon, and then you have the modulation coming into play. And the derivative of eta, so it's dtt epsilon essentially. So you have the linearized operator around epsilon, the damping, the modulation on eta, and G which is the interaction terms. So it's Fr minus the sum of the Fqk. And from this, if you take this equation and do the scalar product with dxqk, and afterwards with if you do the scalar product on epsilon with dxqk and then the scalar product on eta with dxqk, you can get the control of you get the ODEs, the system of ODEs for up to an error for the geometric parameters zk and lk, and this is what you get. Okay, this is what you get at the first step, and also you can do the same thing for AK. So you do this scalar product, and what you get is second order. Okay, so are you really happy with this? You're happy. So if you believe the theorem, this is 1 over t squared. This is 1 over t squared. But this guy, zl plus 1 minus zl, there are distance log t. So this is 1 over t. And okay, so this is damped, but it will tell you that LK is in 1 over t. And if you put it back here, then you have a trouble because you have to integrate 1 over t and it gives you divergence. So it's not enough. And you have to be more careful with this equation. And what does this mean to be more careful is you have to really look at what the interaction of soliton terms, you have to look at the next term, and you get the interaction of the soliton, and this is where the dynamics lie. Okay, and what you gain is you gain a theta, and theta is greater than 1. So here it's integrable in time. Okay. Okay, so I have maybe two more minutes. Is that okay? The first thing,
that's perfectly fine.
So the first thing you have to do is try and decouple the what happens for the epsilon and what happens to the d. And when you try and understand what happens to the epsilon, to the infinite dimension thing, of course, what you will try and use is the damping, but the damping gives you only information on eta. And the first thing you have to do is to cook up a new energy, nonlinear energy functional, that will tells you that both eta and epsilon are damped. And this is, so you take the linearized energy, that is, you take mu is 0, and you do the computation. And okay, in the end, if you do the computation, you have an eta term remaining. So you have some room in eta, and the eta term comes exactly from this guy. So you say, okay, I will perturb a bit, and I will add a small mu epsilon. So you do the computation and you get an epsilon term. So you're really happy. However, there is a bunch of other terms that occur, and they're linear in epsilon, so they're very bad. And what you do is, okay, you try and shake a bit the epsilon term. And there is some kind of algebraic miracle that happens. And if you choose the row like this, actually it cancels out two terms at once. And you get that these two really important results, that this energy essentially retains both the epsilon and eta norm, the Vec epsilon norm, up to the unstable direction. But this is something that you cannot avoid, but because they're present at, they must be present. And also, you regain the damping, that is, the energy is essentially goes exponentially to zero up to a higher order terms. Here you have the epsilon, and then it's quadratic. So this actually is enough for when you have only one soliton. And let me just show you the final thing. The main bootstrap. So so there's a lot of notation that I could not give you, but just give me 1 minute. This n is, what does this proposition mean? It tells you that if you start close enough to a sum of soliton, delta squared near, well, it's delta near soliton, actually, it will remain this way for all times, right? So this controls the epsilon norm, this controls the instability direction, and this controls the soliton, the distance between the solitons. This is really a stability result. And if you think a bit, then how can you expect a stability result when you have instability direction? And this is where we use really, in a very important way, that U is a global solution, because it will give you a long time property, which is this one, that if you start delta near a k-soliton, then actually the L2 norm of the DTU in L2 is small, and it's small for all time. It's the integrated version is small, and this information tells you that you remain near to soliton, and you are able to have this stability result, which is really at the heart of the results. Okay, so sorry to be a bit over time, and thank you for your attention.
Okay, thank you so much, Raphaël. It was really a great talk. I really liked it. Let me ask, are there any questions in the audience?
Yeah, may I have one question?
Yes, please.
Yes. So in the theorem in the slide 10, I mean the first few theorems, and it seems that the result is completely independent from the alpha parameter.
It's independent of many parameters of the alpha, yes.
Yeah. Even that you see in the estimate 2, the t minus 1, of course, is completely independent from alpha. And in that case, I think it also completely independent from alpha, right? So it means that in the analysis, the alpha only interfere in some analysis later on. Even that, of course, clearly alpha is present in the linear operator. So can you explain the role of alpha there?
Oh, yeah, okay. So the alpha is really used. It's really used for this for the L2 bound on DTU. This is really what you need, actually, and you would not need any damping if you give yourself, for example, a solution of a global solution of nonlinear Klein-Gordon, such that you know a priori that it's global and DTU is in L2, then I believe you could run the same argument. Yeah. So the damping really helps you for this, and we no longer use it afterwards, really, because Yeah, of course, it has an impact on the instability direction. It has an impact on the nu, but you don't see it because these are exponential modes that are somehow killed if you want to remain near K soliten.
Okay, thank you. Yeah, maybe that in the analysis we have to have some cancellation, and you put something.
It's just that when the alpha occurs, the alpha occurs in an unstable regime with the exponentially linearly growing term, and our assumption that you have a finite energy solution tells you that actually it kills this phenomenon. So it's killed at this level, and where the alpha also occurs is for the damped term. For the y minus, if you want, but the y minus goes exponentially fast, so it's completely absorbed in these error terms. It occurs at a sub universal at a very lower order term.
Okay, so a small question that in the decay into t-1 is optimal, or you can get better, or it's that it's a sharp decay t-1.
The t-1 is sharp, yes.
Okay. So another question maybe I want to ask that, so if we consider infinite time blow-up, and I remember that you have worked with Hatem-Zak on the construction of multi-soliton.
Yeah.
And I think that it should be happen for this case, right? Because if you consider the finite time blow-up, the damping term and the term used, it will be completely the dominant. That is small perturbation.
Yeah, so actually it's good that you bring that up. It's really linked. The analysis, the end of the analysis, specifically on the ODE thing, is really similar to the one for the blow up on the blow up curve for non-characteristic points. Yes, it's true.
Yeah. Okay, right. Thank you.
Thank you.
Okay, are there other questions? Okay, then thank you again, Raphaël. I think I was planning to ask a similar question to Tian, but okay.
Well, thank you very much, and
I hope you visit us, and maybe we can have further discussions. Hopefully.
Hopefully, yes. Thank you.
Yeah, thank you, Raphaël. It's a nice talk. Thank you. Hope to see you.